Good morning, this is Weli. I'm here to present my paper, Behavior of Smart Steel Column Beam Connection Under Blast Loading. Of course, this is a PhD project under the supervision of Professor Dr. Vigh Laszlo Gergely from the Budapest University of Technology and Economics, Hungary. Well, the contents of my presentation will be about the first outline of this study, then modeling of blast loading, design of SMA shape memory alloy based smart connection, then we try to discuss the effect of strain rate, and we propose a simplified structural design, which is a 2D moment resisting frame structure. Then finite element submodel results will be discussed as well, and finally the conclusion. Let's start with the outline of this study. Well, first of all, we develop a smart steel beam column connection. This is very essential to develop a finite element model, and then numerically we analyze, then we propose conceptual designs of these smart connections. And for this purpose we need blast modeling, blast overpressure modeling. So we have a simplified Kingery air blast calculation in order to draw the time history blast loading profile. And I think it is important to mention that the austenite effect of this nickel titanium shape memory alloy bolts is only included in the 2D moment resisting frame structure analysis. And then the structural components, of course, they are optimized and selected, and they are checked against the ultimate limit state design. The output from the 2D moment resisting frame is used in order to have sub-finite element models. The aim is to provide the high stresses flag shaped loop of these bolts under the effect of blast loading. As we can see here, we can see a very nice high-stresses behavior. This is identical. This is the identical shape of these graphs. Overall, we have a building, a target building. We explode an amount of TNT charges in front of this building, and we analyze the effect of this loading on the structure. Here we can see the 3D structure is simplified to 2D structure, and the blast loading over pressure profile has been drawn and applied on this face of the structure. And then from this 2D model we will have a finite element sub-model analysis. Okay. Modeling of blast load. As I mentioned before, we use simplified Kingery polynomial equation that are very simple for programming, and also they are very accurate. Once we have the blast over pressure on the face of the building or the structure, then hopefully we have a positive and negative phase, but in this case we only consider the positive phase. There are some points I should mention about the modeling of blast loading. First of all, the pressure is applied on the front face only, and there is an assumption that there is no defect in the structure, because if there is, then the inclusion of the negative phase is a must. The accuracy of this approach is within 1%, which is very accurate. For this reason, we need to convert the dynamic load to the static load, and the dynamic load factor is also applied, and it's found it is equal to this factor, which is very small, because the nature of the load is classified as impulse loading. The design of smart connection according to the Eurocode. First of all, we have to classify it according to their stiffness and strength. We found out the connections, both types. We have a semi-rigid connection and partially strength joint. In order to understand more about the energy dissipation and stiffness classification index and the effect of the bolt size on these two factors or results, we have found that increasing or decreasing the bolt size leads to increasing the energy dissipation, which is equal to the area of the force deformation diagram. However, the stiffness classification index is going to be decreased, as can be seen in this figure. This is a very nice indication when it is necessary to design the smart connection. Well, the connection design is based on the Eurocode. So there are many types of failure of the connection according to the Eurocode 3. The majority of them, it happens either it is complete yielding of the flange, or bolt failure with yielding of the flange, or bolt failure. Well, for our case, the bolt failure is our favorite governing failure mode in the connection, because these bolts are responsible to provide the hysteresis behavior. Due to some reasons which I will talk about it later in next slide, we have two configurations with different sizes, and the material modeling and geometrical characteristics is given in this table. IPE 400 and 500 are used for the beams. HEA 500 and 400 are used for the columns. And finally, the material characteristics for the bolts are also given here. The effect of the strain rate, since it has effect on the recentering capacity and energy dissipation of this material, so we had to investigate whether our bolts or smart connection is still capable of providing hysteresis behavior. Well, after the investigation and an intensive literature review, we found out that yes, these models can provide the recentering capacity, good recentering capacity, and energy dissipation when the strain rate is below 1001 of a second. And this strain rate is based on the analytical calculation, which is taken from the Eurocode design and the applied loading velocity. This is the characteristics of the SMA bolts after the inclusion of the strain rate effect. Well, this is also, these values have been calculated according to the curve fitting analysis from the literature review. Then we found out these new values should be used in the finite element model. And then for the steel components, we follow the Cooper-Simon equations as can be seen in these two equations here. Then we come to a point which we need to have a 2D moment resisting frame. So we said we have simplified structural design. Of course, this is also based on the Eurocode, and equivalent static load over pressure has been applied. The optimal cross-section have been selected after few iterations, and the effect of the austenite phase has been included only. Well, once we have the analysis of the 2D frame, then we need to say that the inclusion of the effect of this austenite phase of the SMA bolts, nickel titanium shaped memory alloy bolts, has been included in the 2D analysis by having these end released beams. So it's like a spring in axis VM here. Then the only austenite phase is included. Once we apply the load, after a few iterations, we have the section sizes. That's why we have two section sizes, the bigger one used in the lower columns, the smaller in the upper columns. And then we have the numerical local model, which is being taken from the global model, and the outputs here applied as well. Then we have the finite element model or submodels. So this submodels results, we notice that we have somehow considerable deformation at the lower parts. That's why we can't expect a very nice hysteresis behavior. So this is for both models, and we can see that the stress concentration is still in the bolts, which is very good, but we have somehow stress concentration in the steel components. The force deformation can be seen here for the first model and the second joint configuration as well. And this is this shape that we have. We consider it's not fully high-stress behavior. That is why we certainly say we have residual deformation in the steel components. And the result is compared with the steel balls, and we found out the residual deformation in the steel ball is 2.5%, while in the SMA balls is 0.8%. And this is the stress strain diagram for both, and this is the force deformation curve for the steel balls and for the SMA balls, and the difference is clearly can be seen here. To sum up, we can say that these type of connection are capable to provide high stress behavior, and they are better in terms of energy dissipation and recentering capacity. Then we can say that different design configuration leads to connection improvement as we have proceeded in the next step since 2020. It is important to ensure connection third failure as described in the EC3, or let's say the ball failure, and to propose some conceptual design further study is needed. And since 2020, as I said, we have progressed and improved the connection models, and few articles have been published. Thank you very much for your attention, and I will be in the conference to answer your questions. Thank you.